should my slideshow be? Yeah, visible?
Yep.
Yeah.
Okay. So basically the topic that I've picked up is from a paper called Decompression for Dense Point Cloud Maps. This was published last year by one very leading authority in robotics and computer vision, Cyrill Stachniss. And here basically for large point cloud maps, they're providing a way to compress it intensely so that you can transmit it very easily. So I'll start off with the background. For those of you who are not aware, point clouds are a way to represent 3D data with points. So let's say there is this chair, right? In a 3D model, it would be like a mesh or something. And with point clouds, you're literally just sampling the mesh at different points. So it gives you like a set of x1, y1, z1, x2, y2, z2, x3, y3, z2 till n points. That depends on how densely you sample it. And point clouds have two very important properties that they're invariant. So like the set that I have given here, x1, y1, z1, x2, y2, z2, even if I change the order, so if it's like x3, y3, z3 first, and then it's x1, y1, z1, it does not really change the point cloud, right? Because when you're visualizing it, it's essentially the same thing. And the second thing is it should be invariant to rigid transformations. So let's say when you're rotating the chair, right, your points will change. They'll get multiplied with a rotation value, right? X cos theta, y sin theta. But the chair will still be a chair. So that should not change. Or when you're translating it, let's say I'm moving it by 5 meters here. So it'll be x1 plus 5, y1 plus 5, but it's still a chair. So that's what a point cloud essentially is. Is this clear, the background?
Yes, it is clear. But everybody else.
Yep, clear.
Just feel free to like just interrupt me at any point of time because this is a slightly complex topic.
Yeah, Jay, one question.
Mhm.
Do you know other representations where this property doesn't really hold?
Meshes. So meshes are basically vertices, triangular vertices, and how they're represented is like you'll have vertices x1, y1, z1, x2, y2, z2, x3, y3, z3, and you'll have faces which are composed of three properties, three vertices. So like this is the only 3D data which has these properties. All other data representations don't have these properties, like voxels, for example. So it's just point clouds. Is that fine?
So you're saying that triangular representations are not permutation invariant? Okay,
yeah, like
they're not.
Yeah. Oh, meshes are not, right. If you change something in a mesh, it will become something deformed.
Okay.
Okay, so anyway, that was just a primer. And the basic motivation is, so like let's say you have a self-driving car and your lidar scan literally takes in an input of 40.7 gigabytes per scan, and that is obviously very expensive to transmit, right? So what you do is you have an encoder that compresses it and a decoder which then reconstructs it at the receiver end. So from this is picked up from the paper, and they actually managed to bring it down to 0.2 gigs, so 200 MB. And this is their approach. So overall, let's just discuss it broadly so that it's not that complicated. Essentially, you can think of it as an autoencoder structure, right? So what you're doing is your input is basically your point cloud. And let's, for simplicity's sake, consider that they're not colored, right? This is just visualized, but let's say they're all of the same color. Let's say white, 255, 255, 255. And so this is your input feature set which is flattened, and you have one single feature which is the same color, white. And now what you're doing is you're basically ignore the fine details, but you're basically downsampling it, making it smaller, 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 just like an autoencoder. And then once this is encoded, you store it, and at the receiver end, you start decompressing it. And then there is a loss function. I'll go through all of that, but is the broad architecture understandable?
Yeah, it seems fine. I'm just curious as to why you're dealing with 3D convolutions here.
Yeah, I'll come over that. But overall, this is not a 3D convolution, by the way, but you just got the idea, right? That it's like it's an autoencoder structure, more or less.
Okay.
Yeah. So tell you the encoder structure now. So standard encoder structures. So this is like a 2D encoder. This is your standard image encoder, right? Your basically your input is some grid. You have a kernel. You multiply it, and you get the output, right? Now a KP-conv layer is essentially the same thing, but in a 3D space. So let's say you have this input point set, right? For each point, you have a kernel, and these kernels are basically a 2D Gaussian kernel, and it has points sampled in between at regular intervals. So what you're doing is you're essentially multiplying it with the distance, right? So let's say this point, you'll calculate the distance, the 2D distance between each of these points, and then you'll take the max according to this formula, and you just basically get the output, just like a 2D kernel. And then you basically, once you get, yeah, go on.
Yeah, I have a question. So your kernel is point sampled from a Gaussian?
No, your kernel is basically for, so let's say, since this is 2D, your kernel is like a 2D Gaussian circle, and you have points inside it.
Yes, some random points inside it.
Yeah, you can have them random, you can keep them anyhow. There is what they've done is they've symmetrically kept them. But the paper, the
Okay.
KP-conv paper basically says you can actually learn the places also. But let's say that they're just equally placed symmetrically over the distance, just like the 2D kernel. So, and the other procedure is exactly the same. You just take the distance, multiply, you get the output. Is that fair?
So is it the shortest distance or the max distance?
No, you not the max distance. You literally just take the distance from each point in the kernel. So let's say this point here. Oh, wait. This point here, you project it onto this kernel, so it's on the same plane, and then you literally calculate the distances between each point, and then you add them. Okay.
You add them. Okay.
Yeah, you add all the distances. Just like here, you add all the features, right? So, okay, I'll go ahead. And then you're basically repeatedly downsampling it, increasing the feature size, just like a normal autoencoder structure. And what they do at the last layer, which is here, if you see, N3 is the number of points at this layer, and 32 is the feature size, right? So you downsample it again, like normal autoencoder, you get any number of points. And so you have any number of points, and you have 32 features. So how do they bring that to 3 features? So what they've done is this, they've literally used a normal MLP layer, which is like your normal ANN, and taken each point and that corresponding feature and calculated the output feature set. Is that Clear?
Can you repeat the last part?
Yeah, so basically, let's say you have 100 points and each point has 32 features size, okay? So and you're trying to get an embedding space. Let's say in the embedding space, you want only 50 points. So you downsample it normally, you get 50 points, but now those 50 points still have 32 features, right? But you want 3 features only per point. So what you do is, for each point, you have an XYZ coordinate and you have a 32 feature representation. You pass these features to an ANN. So basically 32 features plus 3 coordinates. So 35 parameters you'll pass through a normal neural network, artificial neural network. And the output of that MLP is three basically neurons that give you the feature size.
Okay, makes sense.
Mhm. So you get the embedding space, and that is 3. Now, once you have this embedding space, at the decoder part, this is the real magical stuff that happens. So you're basically now wanting to again decompress it and reconstruct it, right? So what they do is, for each point, they pass it through a decoder network that gives out say 3 points. In the paper they use one point and they build 3 points, and how they build that 3 points is quite interesting. So they take your each point and its corresponding feature set, and they'll again pass it through 2 MLPs. One MLP will predict the feature set, and the other MLP will actually predict the displacement of the new point from the previous point. So let's say you have a point centered at 0, 0, 0, and it has some sort of feature, let's say 255, 255, 255. What the first MLP will do, the upper one, is it will predict the feature set for the new point. So let's say 255, 255, 255 will become some sort of 128, 128, 128. And the second part will actually predict a displacement. This is quite interesting. So what will predict is, say from 0, 0, 0, my new point has to be at say 0, 0, 1. So the displacement will be 1 in the Z direction. So that is what the second MLP predicts. And then you're basically just adding the previous point to get the actual coordinate. And this is repeated 3 times. So for each point, you get 3 new points. So we're increasing it by a factor of 3. So once you keep on upsampling this, if you notice this, from any you get k number of points, which is kne. So from let's say 50, if I sample it 3 times, you get 150 points. Then at the next layer, you will get 150 into 3, which is 450 points. Then 450 into 3, and then whatever 450 into 9. And that is your final output layer. And you can observe that this feature size is again 32. And they do the same trick again. They'll pass it through a normal ANN, and they'll get a compressed form of output. Not compressed, but basically reduce the feature set, which was done here, 32 to 3. Now, once you have the 2 point cloud sets, the input point cloud set, which is this, and the output point cloud set here, you want to obviously train the network. So how do you do that? So there is something called as a chamfer distance, wherein you can think of it. First, you associate the points for 2 point cloud sets. So let's say there are 50 points in my first point cloud, and you have 50 points in the second point cloud. You first say that, okay, the first point in my first point cloud set is the third point in the second point cloud set. then it's basically just a mapping, right? One-to-one mapping. And once that mapping is done, you calculate the Euclidean distance between each of those points and just add it up. And that gives you the loss function, basically. And then you just back propagate it all the way through.
Give me a second. Could you just go back? I didn't quite understand the loss function. So you're saying it's a Euclidean distance between P and P out, and what is Pj over here?
Where is Pj?
I'm looking at the formula.
That's just Ij. This is just a general formula of the chamfer loss. This is the chamfer association. Let's just consider this P in and P out. Okay. So the first part of the formula considers it first P in and P out. So what it does is, for each point in the input point cloud, you will find the closest point in the second point cloud, right?
Okay.
So if your first point was 0, 0, 0, and the closest point to that was 0, 0, 1, which is what we reconstructed, that is what it would be associated with, and not say 1, 1, 1, because that's farther away.
So your 2 point cloud sets are your prediction and target.
Yeah.
And you are saying that it is the minimum. Okay. So it doesn't have to be a 1-1 mapping. It's just the minimum distance, right? But won't this loss take n square time to find a minimum distance itself?
Yeah, exactly. It takes a quadratic time. That is, you can say, a problem, but this is the most optimal, you can say, generally chamfer distance that is used. But it does take quadratic time complexity.
Unless the points are sorted, but that will also take some time.
Yeah.
Isn't the Earth mover's distance a better metric than chamfer? Because it has visual
Earth
quality
mover's
as well.
distance. It really depends. Earth mover's distance has been used in some cases, but I don't know. Somehow, chamfer distance is just generally, by tradition, used in this, and it's kind of like easier to compute than EM.
Okay.
So Earth mover's distance is what exactly?
Earth mover's distance is something like, let's say you have two Gaussian distributions, okay? Let's say first one is centered at 0 and has a standard deviation of 2. And the second Gaussian distribution, let's say it's centered at 1 and it has a standard deviation of 3. So what it essentially tries to find is, what is the minimum number of, and let's say this Gaussian distribution is discretized in terms of boxes. Okay. So what EM basically does is it asks the question, what is the distance in terms of moving the boxes to make the distributions identical? I can probably show a better
no, I know, I understood what you're saying. Yeah.
I'll just show it nevertheless.
Oh, it's kind of like a discretized KL divergence is what you're saying.
Something like that. Wait, I'll just show you. Yeah, so in this case, basically, you have two distributions, right? X and Y. What EM is basically calculating is how much, and let's say there are dirt piles. So how much distance or dirt do I have to move by how much to make X the same like this Y thing?
You're doing it in one direction, right? Because otherwise this problem becomes dynamic programming or something.
It's one direction. It's only this, right? If you see, compare it in this direction only. This might be a better visualization.
Hmm.
Anyway, so EM is something like that.
Hmm.
And anyway, so this is the loss function, and then they just train it end to end. And so the results that we get are quite good.
I think the reason you wouldn't want to use EM is because we don't have our point clouds to be distributions, right? They are discrete values, and if
You
we try
convert
to
them, right?
change it, convert them,
What?
Like you form a probability distribution of them.
that
Yeah,
won't
Earth movers can
encompass.
be no, Earth movers can still be used to compare point clouds. It's basically like you have to consider it as a like like I said, right, a dirt kind of thing. So even distributions, that is continuous, but here you're calculating in a discrete sense. So in a discrete sense, you're literally just taking the distance between 1 and 2 point cloud sets. But for a distribution, you'll have to integrate that.
Okay.
So anyway, the quantitative results that we get are much better. So some standard previous point cloud compression techniques are Draco and MPEG octree based. And you can see that as we decrease even like the bits per point, you have still very good results. So DE is the distance between the first and the second point cloud, and you can see that even when you have very low bits per point, you have very good reconstruction results. So DE is basically the more or less the chamfer distance. D perpendicular is another metric, and IOU is occupancy based metric. So you have a occupancy grid, and you're seeing how filled is each occupancy grid cell. So in all cases, even when you have low bit rates, a low bit per points, you have the best results. And these are some quantitative results that might actually give you a better idea. Even for like 0.16 bit per points, you have the best result, which is quite close to the input point cloud. And they also did a study where they found out that this generalizes very well across data sets. So they actually trained it on one data set and they tested it on another data set, and the results were still the same. So yeah, this is more or less the paper. Some things that I had thought of is so the current approach only works for plain point clouds and it does not have color features. I had actually reached out to the author of this paper also, and he said that this would be one area that he would like to tackle it in the future, but he didn't really. And the second one is, if you see that this embedding space here, you can't really do anything with it except just transmit it. And let's say at the output end, you want to visualize it from another angle, you'll have to rotate every point, right? So the computation increases at the output side. But I'm curious to find out whether if I can have some sort of representation, which when multiplied here itself, I don't have to kind of multiply it at the output end. Those were like two major things, and you can probably experiment with loss functions and see how sampling can be done. So more or less that is it. If you guys have any questions or ideas, we can discuss that.
So in inference time, or rather whenever we are trying to get the decompressed representations, we just use the decoder. That's the selling point of this paper, right?
Sorry, come again.
Uh, During inference time, when we want to just load the uncompressed output or decompressed output, we use the decoder. Like we just take. Okay.
Yeah. And this is
Hmm.
just one-time training, so you don't have to train it over multiple point clouds every time. It's just you train it once, and then every lidar scan that you get, you can transmit it very, very quickly. That is the selling point.
So another question is, do the other works over here allow for rotation of point clouds in the shared embedding space?
None of them currently do. That is one thing that no paper yet has tackled.
That is a pretty interesting uh, thing to do, right? Like,
Yeah, some sort of explainable or some sort of latent compression that can actually be, multiplied upon, and then you don't have to
hmm.
multiply it again
So,
with the output.
I mean, I'm just thinking over here, but have you heard of deep dream?
Deep?
Deep dream kind of thing where you perform activations on the input given the output. Deep dream, not heard of it.
Is it that thing that generates like trippy kind of
Very
images?
psychedelic stuff, yes.
Yeah, I got it. This stuff, right?
Yeah.
Mhm.
So
So
in deep
what?
dream, what they do is they increase the activations and then they see what is the change in input. But over here, instead of changing the activations or increasing the activations, we just change the orientation of the output. Can we achieve something like that? Good.
One thing is you won't really want to change the orientation of the output too much, because
Hmm.
what happens is, if I'm, let's say, looking at it from this side,
Hmm.
and if I change the orientation so that, let's say, you're just basically uh, tilting it, but if you get the same reconstruction output, that's actually wrong, right? Because you want the angle to be preserved.
Is there any in this study? Was there any kind of similar to how we have an attention map in attention-based studies? Do we have some kind of mapping decoder map or something like activation map over here?
Uh, Not really. They don't. But their claim is basically, since they test it on a completely different data set, it generalizes.
Hmm. No, the reason I was asking that is because it could be explainable as to how exactly do you transform the embedding space to achieve a rotation. So,
Yeah, that would actually be so. One important point is the the embedding space itself are more or less points, because
hmm,
it's not a completely latent representation as in for images, right? These are
hmm,
points. If you see this, uh,
yeah,
these are points, they're just subsampled points. So the points essentially stay the same. Some
hmm,
points stay the same. And then the remaining features are basically capturing the geometrical relationships.
hmm.
I
Any
see
other
that,
question?
yeah, probably either it's clear completely or nobody has understood it. And I'm inclined to think it's the latter.
I understood like parts of it, but definitely not the whole thing. It's good to know what's going on out there.
Yeah,
See, I
it's
have
Yeah, same. Even I had like little trouble following what you were saying.
Yeah, that's
Yeah.
fine. I was expecting that. But more or less, in a gist, if I explain it, it's basically you're compressing it via an auto-encoded structure, and then you're decompressing it. You can go over the details in the paper, which will probably make you understand better, but that is essentially what the paper is. You're just reducing the points with each layer and capturing the geometrical relationships.
yeah. Actually, I think we have like around 6 minutes remaining. So I'm just thinking of an approach which we could use. Wow, this is beautiful. What's this? But basically, one simple way to firstly, is the code open sourced for this model?
Yeah, it is. I can share it.
And secondly, what is their compute for this? I'm seeing every image is like 40 gigabytes. It's insane. So how exactly do they work with
I
this?
trained it on a GTX 1080, if I'm not wrong.
No way.
Yeah, yeah. Let me see. Or maybe it might be more. I'm not sure. Let me just check.
It's 40 gigs, man.
RTX 2080. My bad.
RTX. Okay.
So yeah,
But
RTX
but still,
2080.
storage of such a data set itself would be like tens of terabytes.
Not tens of terabytes. It's probably like 500, 1 terabyte.
Okay. So I was just
The
thinking
point
if we can
is, yeah, go on.
I was just thinking we could augment the images, right? Once you have your pre-training of or your encoder and decoder done, we can augment the images with their rotations and get all the rotations for every image and the shared representation, and then use another network in order to feed in, let's say, your encoder representation E1 plus some kind of rotation matrix as the input, and you get the representation, and you get E2 as your output. So another autoencoder just for rotations.
Oh, so you're saying that here, once you have this, you kind of
Yeah,
manipulate this area and just pass it out again.
yeah. Like using another autoencoder or another
Mhm.
denoising autoencoder. Yeah.
Yeah, that would be quite interesting.
Hmm. My only concern as to why I'll not actually go ahead with this is because I don't have that kind of storage.
Yeah, fair enough. Fair enough point. But you actually don't need. So here they did it with very big point cloud maps, like, but you have point clouds of smaller sizes as well.
Hmm.
Here they did it for like an industrial scale kind of thing, but you have this ShapeNet data set. I'm not sure if you've heard of it.
Hmm.
So that is not very dense. You can have the smaller kind of things. So this will probably be like 5 to 10 gigs.